Okay, folks, so shifting gears, getting into more conceptual, qualitative stuff. So let's talk about alloys. Okay, so a few definitions first. So an alloy is a blend of a host metal and one or more other elements, which may or may not be metals, that are added to change the property of the host metal. So when we talk about this host metal, okay, that I'll say is majority of the solid. Okay, so when we talk about an alloy, for example, here's a couple pictures of brass and bronze. Okay, so I'm pretty sure this one here is brass and this one is bronze. The vast majority of brass and bronze is copper. Okay, so copper equals the host metal for these two alloys, which maybe is not all that surprising when you look at how these alloys appear. They do look like copper, okay? But now to make brass and bronze, other elements are added to this copper, which changes the properties of the original copper, and we now have a new material that we call an alloy, okay? Such as brass or bronze. So we could have two different types of alloys we're going to talk about in this class: substitutional alloy and interstitial alloy. So a substitutional alloy is an alloy in which atoms of the non-host metal replace host atoms in the crystal lattice. Okay, so and that kind of makes good sense based on the name. Substitutional is a good way to think about that. So we're plucking various atoms out of the unit cell and replacing them with different types of atoms. Okay. And then there's an interstitial alloy. Interstitial alloy. An alloy in which atoms of the added element occupy the spaces between atoms of the host. So what that means now is we're not replacing host atoms with non-host atoms. We're smashing non-host atoms in between the little spaces that might exist between the host atoms. Okay, so here's a couple of pictures. So I've already talked about brass and bronze. And I want you to recognize that brass and bronze are both substitutional alloys. So know those examples: bronze and brass, where once again copper is the main host element. And you can see here in bronze, this is made up of mostly copper and occasionally replacing a copper atom with tin. Okay. And so what's the advantage of doing this? Well, if we look at just copper, and we recall that copper is one of these FCC, right? So let's back up here to my periodic table, right? Remember I talked about this, copper, FCC, it's malleable, it's soft, and that's because it has those slip planes in the FCC lattice. I'll just kind of draw that right here. And what we're able to do, you can see here that quite easily you are able to bend copper. And if you've never done this before, I actually find it to be quite satisfying, because you've got like this metal pipe and you have this impression like, oh, this is a piece of metal. Like I can't really bend this thing, right? But you could totally fake your friends out with like a He-Man, Hulk smash kind of a thing. And it's so easy to bend copper. It takes little to no effort at all, which is why it's used for plumbing and wires. It's very easy to bend and manipulate copper. However, this also makes it easy to break copper, right? We can bend it to the point where it just becomes completely deformed and not really usable anymore. So we have to be careful when we bend it. Bronze, on the other hand, is actually much harder. And the reason for that now is because if you imagine our slip plane, right? So before, if these were all copper atoms, we'd have this nice, beautiful parallel slip plane. But you can see that the tin atom is just a little bit bigger than copper. So let's find that on my periodic table again. Okay, so tin is Sn, and of course, is it marked on this periodic table? No, it's not. Oh, there it is. Okay, right, lovely. So there's my tin. So you can see it's lower down on the table, so it is bigger. Okay, so that means now this slip plane is disrupted, and these planes can't roll over each other as easily. So now this bronze is much, much harder to manipulate, and it can be used in more structural applications. For example, if you have like this faucet right here made out of bronze, we don't want your kid to be able to like bend your faucet in half, right? And then same with brass. I'm not showing you the example here, but brass is much harder than just plain copper. And so that's why it would work much better as a cooking pot than plain copper, because you might be able to bend your pure copper pot, but maybe not your brass pot, okay? So be familiar with these two examples as substitutional alloys. And then the example that we'll talk about with an interstitial alloy is steel. Okay, so I'm not going to spend a whole lot of time getting into these details about octahedral holes and tetrahedral holes. If we stare really closely, we could count up an octahedral hole by looking at an AB lattice, flipping it on its side, and then we can literally see there's 1, 2, 3, 4, 5, 6 atoms surrounding that hole. And because there's 6 atoms surrounding that hole, we call it octahedral, okay? And here we can see some information about if something is going to adopt an octahedral or even perhaps a tetrahedral hole. So for example, here would be a tetrahedral hole where it's 4 atoms surrounding a hole, right? That makes it tetrahedral. So you can see the smaller is the non-host atom relative to the host atom. So I'll rewrite that. That's the radius of the non-host atom over the radius of the host atom. So you can see the smaller that is, the smaller are the holes that it will adopt. Okay, so octahedral holes are adopted when the non-host atom is just a little bit bigger. And that's what gives us these names, which is, recall, the hexagonal closest packed or cubic closest packed. Okay. And so now here is a picture of our steel. Steel is mostly made up of iron. And we note here that if we shove a carbon atom in between the iron atoms, so in one of those holes, it makes our alloy steel. Okay? And iron is already a fairly strong material on its own. Steel is even stronger. And this is, of course, what led to the building revolution in the Americas, and specifically North America in the 1930s with the skyscraper movement, right? All of those buildings being made up of steel, and they're still around and structurally viable today. Okay, so there are 2 main different types of steel that are used. There's actually much more than that, but these are like the 2 main ones. You hear it often referred to as 304 stainless or 316 stainless, and that is referring to stainless steel. And of course, it would help if I had a stainless steel example in front of me right now, but I don't. But guaranteed, all of you have some sort of stainless steel appliance, grill, or whatever in your house, in your car, something, right? It's that lovely, shiny metal, okay? So stainless steel is chemically resistant. So not only is it structurally sound, but it does a really good job of resisting oxidation or rusting. And that's mostly from the addition of chromium. So you notice both 304 and 316 have a good amount of chromium in them. and a good amount of nickel. 316, the only difference is it has a little bit of molybdenum. And so often what we see with 316, this is the really fancy stuff that we see with like medical application. So perhaps like the syringes, the metal tip on a syringe is typically 316 stainless, or any type of material that you really want to not rust or react away, something that you want to be preserved. That's used for 316. Something like your barbecue is going to be made up of 304, or even structural material might be made up of 304. And it's just that tiny little bit of molybdenum that makes a difference. Okay, folks. So once again, just kind of be familiar with these examples of interstitial alloys, so in other words, steel, and substitutional alloys, so brass and bronze.